Assalamualaikum. My name is Fathin Noorshafirah, and today I will present our group project title, the Precision Conveyor System. So the objective of this project is to design and simulate a DC motor control system for a conveyor belt using light simulating and syndicate. So the main goal is to make sure the conveyor belt maintains a constant speed even when the load changes suddenly. So in this simulation, the target motor speed is set to 150 radians per second, and the sudden load disturbance is applied at 5 seconds. So this is the complete simulated model for the conveyor motor control system. So the system uses a DC motor block which represent the motor driving the conveyor belt. So the motor is connected to the inertia block, which represent the rotational load of the conveyor belt. Uh, a, a rotational damper is also included to represent friction and damping in the mechanical system. So the constant block provides the target speed, which is 150 radians per second. The sum block compares the set point with the actual motor speed and calculates the error. The error is sent to the PID controller. The PID controller calculates the required control signal to reduce the error and maintain the target speed. The control signal passes through a Simulink is converter because Simulink signal needs to be converted into physical signals before entering the syncap system. The signal then controls the control voltage source, which supplies voltage to the DC motor. To measure the motor speed, the ideal rotational motion sensor is connected to the motor shaft. The sensor measures the angular velocity of the motor. Since the sensor output is a physical signal, a PS Simulink converter is used to convert it back into a normal Simulink signal. This peak signal is then fed back to the sun block. This creates a closed loop feedback system. The max block is used to combine the set point and actual speed signals so both can be displayed on the same scope. The unused angular position output from the sensor is connected to the PS terminator. To simulate a sudden load on the conveyor belt, a step block is used. In this model, the step block represents the load disturbance. The disturbance is applied at 5 seconds. The step block setting or step time equal to 5 seconds. Initial value 0. Final value negative 0.7. So the disturbance signal passes through another Simulink PS converter and is connected to the ideal torture sources. So the ideal torture sources applies torture to the motor shaft representing an item suddenly being dropped onto the conveyor belt. So now I will show the PID controller settings. So the final PID values used in this project are the proportional uh, gain equal to 20, integral gain 40, derivative gain equal to 2. So this value was selected because they produce the best response in the simulation. With this value, the motor can recover after the disturbance and return close to the target speed. So now I will run the simulation. So the simulation time is set to 30 seconds. So during the simulation, the PID controller continues check the speed error. If the actual speed is lower or higher than the target speed, the controller adjusts the motor voltage automatically. So this allows the motor to maintain the desired speed even when the disturbance occurs. So now I will open the scope showing the set point and actual motor speed. So in this graph, the yellow line is the actual speed, which is fixed at 150 radians per second. So the blue line represents the set point. So at the beginning of the simulation, the motor starts from zero and accelerates towards the target speed. So this is a small overshoot at the start, which is normal for the PID control system. So at 5 seconds, uh, so at 5 seconds, the turbines loaded is applied. So when the loaded is applied, the actual motor speed drop because the motor suddenly needs more torque to overcome the extra load. So the speed dropped to around 70 radians per second. So after that, the PID controller detects the speed error and increases the control effort. So because of this, the motor speed start to recover. The speed then return close to the target value of 150 radians per second and becomes stable again. So this shows that the motor successfully recovers from the disturbance. So for the open loop system, the motor runs using a constant voltage without a controller. So when the disturbance load is applied, the motor speed drop because there is no feedback system to correct the error. So the motor continue. The motor cannot automatically adjust the voltage, so the speed does not recover properly. So for the closed loop system, the PID controller use feedback from the speed sensor. So when the speed drop after the disturbance, the controller detect the error and adjust the motor voltage. So this make the closed loop system much better because it can recover and maintain the target speed.
Next, I will show the current response graph. The motor current is measured using the current sensor. At startup, the motor current is high because the motor needs more power to accelerate the rest. From the rest, after the motor reaches steady state speed, the current becomes more stable. When the disturbance is applied at 5 seconds, the current changes because the motor needs additional torque to handle the extra load. This shows that the motor draws more current during the startup and disturbance condition, while the steady state current is more stable. The model includes a solver configuration block because SIMScape physical network require a solver to calculate the electrical and mechanical equation. In this simulation, no algebraic loop error occurred, so no special algebraic loop handling was required. For the disturbance, the step block has zero crossing detection enabled. Zero crossing detection helps Simulink accurately detect the exact time when the disturbance changes at 5 seconds. This is important because the disturbance happens suddenly and the simulation needs to capture the transition response correctly. The model runs successfully without solver errors or convergence problem. In conclusion, the DC motor control system for the precision conveyor system was successfully designed and simulated using MATLAB Simulink and SIMScape. The open loop system was not able to maintain the motor speed properly when the load changed. After implementing the PID controller, the system was able to detect the speed error and adjust the motor voltage automatically. The final PID values used were P equals to 20, I equals to 40, and D equals to 2. When the disturbance was applied at 5 seconds, the motor speed dropped, but the PID controller helped the motor recover and return close to the target speed of 150 radians per second. The current analysis also showed that the motor requires a higher current during startup and disturbance condition. Overall, the closed-loop PID controller successfully improved the stability, disturbance recovery, and also the performance of the conveyor system. Thank you so much. Next, I will show the current response graph.